Hello guys, and welcome to the long-awaited video on examination reviews. So we are going to be looking at an important topic in frequency domain analysis and control systems called the Nyquist criteria for stability of a closed loop control system. That's the Z equal to N plus P. All these characters might seem a little strange to you, but I'm trusting it is not. But not to worry, by the end of this video, you will be an expert in stating and analyzing Nyquist criteria for stability. If you're just joining my channel for the first time, this channel is called Make Me a Solution. Please subscribe to my channel and stay tuned for explosive content that will make you feel like a good student. So hit the notification bell to stay updated and like this video. We're going to be handling a series of examination review questions. So I'll charge you to follow these exam questions in the order I release the video, or in the order the video appears in the playlist. So if you're ready and you've liked my video and you've subscribed, let's dive in and let's analyze, let's break down Nyquist criteria for stability. Now, first of all, I need to deviate a little before I dive into the content properly. I need to tell you something very important. Assuming you're given transfer function, let's say you're given a transfer function, g of x is equal to, let me see, something like 2 divided by, 2 all over s plus 4, s plus 5, and s plus 2. Okay, let me just change this one to a k, for instance. When you're given a transfer function in this form, before you analyze or before you perform any analysis, any frequency domain analysis on this kind of transfer function, it is important to convert it to standard form. So we are converting it to standard form, or sometimes they call it standard time constant form. Okay, standard time constant. So the standard time constant equivalent of this system is going to be something like this, maybe some k prime all over. You will now have 1 plus t1s, and you now have 1 plus t2s and 1 plus t3s. So that will be the standard time constant equivalent of this one. So let's quickly run over it. So g of s is now going to be, you have k all over. If you want to convert this to standard time constant form, you factor out 4, and you factor out 4, you will have 4 brackets, 4 into 4, 1 plus 4 into s is going to give you 1 over 4s, like this. So you do the same thing on this part, 5 bracket 1 plus 1 over 5s. Okay, I just swapped the position, and finally you factor out 2, you have 2 brackets, 2 into 2, 1, then plus 2 into s is 1 over 2s. So if you've done it like this, you can now have your g of s is now going to be, if you rearrange, you will have 1 over 4 dot 1 over 5 dot 1 over 2k on the numerator position. Okay, so what I just did was I moved all these numbers to the numerator position. Then what I now have here is 1 plus 1 over 4 becomes a 0.25s, then 1 over 5 becomes a 0.2, and finally 1 over 2 becomes 0.5. Is that okay? So this is not all. Another thing we need to note is that when you're expressing it in the standard time constant form, it is important to arrange in order of decreasing t, decreasing t, that's decreasing time constant. So the final expression is going to be k all over, you will have k into 1 over 4 dot 1 over 5 dot 1 over 2 into, the biggest one is 0.5, so I have 1 plus 0.5s. Okay, then following is 0.25, 1 plus 0.25s, and finally The smallest time constant is the 0.21 plus 0.2s. Is that okay? So this is how we are going to be writing our systems. Anytime I'm giving a control system or a transfer function or an open loop transfer function, however I'm giving, I have to make sure that I express it in the standard time constant form, whereby the time constants, which are the coefficients of s, are written in decreasing order, and you always have a 1 here, so it must always be a 1. So you have to manipulate the equation so that you get it in this form. So I hope you got that. So if you're ready, we're going to dive in to our lesson proper. Now we are looking at Nyquist criteria for stability of a closed loop control system, and Z is equal to N plus P. Z is equal to closed loop poles, right? N is number of entanglements, and P is number of open loop poles. Okay, so this is Nyquist criteria. Z is equal to N plus P. So in 1932, someone called Cauchy developed a principle that we call Cauchy's principle of arguments. The formula is N is equal to Z minus P. So Nyquist in the year 1932, he worked on this particular Cauchy's principle of argument in order to develop what we call the Nyquist stability criteria, and he now reinvented it, and we now know it like this. Sometimes they use this expression, sometimes they use this expression, but at the end of the day we are going to study and understand what the N equal to Z minus P means, or the Z equal to N plus P means. So beginning with the first definition, at least a control system will be stable if its transfer function has no poles occurring on the right hand side of the entire S-plane. So the right hand side of the entire S-plane, the S-plane can be drawn like this. Sorry, this is your S-plane. Okay, so this is the imaginary axis and this is the real axis. So anytime you solve a control system and you solve the characteristic equation, if a pole occurs on this side, okay, on this side, that means your system is unstable. So these are all right hand side poles, okay, right hand side poles. So we want to avoid this in control system as much as possible. If our system must be stable, anytime we solve the characteristic equation of our control system's transfer function, we want all the poles to occur on the left hand side, that's the negative side of the S plane. Is that okay? The S plane is a complex plane that plots alpha plus j beta, where alpha is a real number and beta is an imaginary number, like this. Okay, so S is equal to alpha plus j beta. So this is like the expansion of S in complex number form. So you always plot it real axis versus imaginary axis. So anytime you solve your control system's characteristic equation, anytime you get the roots of the characteristic equation occurring on the right hand side of the S plane, whether the positive half, that's the first quadrant, or the fourth quadrant. Okay, these quadrants 1, 2, 3, and 4. So if your poles occur on quadrant 1 and quadrant 4, okay, your system is unstable. But if it occurs in quadrant 2 and quadrant 3, your system is stable. If, however, you have poles occurring on the y-axis or on the imaginary axis, then your system is marginally stable. So you have unstable, stable, then marginally stable. So you can see the difference, right? So when we are talking about control systems, it has to be in such a way that no poles occur on the right hand side of the entire S-plane. If at all, our system should be stable. So this is the first definition. So assuming you're given this control system, for instance, you're all familiar with this diagram. So in this diagram, we have our R of S, which is the control input, then this is the control output C of S. Then this is like the forward path transfer function, this is the feedback transfer function. Okay, then you know that if you are very familiar with your block diagram reduction technique, this system can also resolve to this one. So this is the combination of this system. Now GH of S is still the same thing as G of S times h of s. So I just used a shorthand gh of s, okay, to denote it. So this is the combination of this control system. So when we have a control system like this, which resolve to this particular stuff, we call this one the closed loop. This is open loop transfer function. G of s alone is open loop transfer function, okay. Or sometimes in some textbooks you might see them using g of s and h of s. Just the product of g of s and h of s is the open loop transfer function. Now g of s will be the open loop transfer function if h of s is unity. If h of s is equal to 1, okay, we'll call it open loop transfer function, and then you call it a unity feedback system. But the closed loop transfer function is g of s divided by 1 plus g of s h of s. Okay, so this is the one that we are most interested in when we are analyzing stability, the closed loop transfer function. And we want to make sure that transfer function, which is defined as output over input, okay, the characteristic polynomial, which is the denominator. When you express your denominator in terms of s, you will have this. And to solve this characteristic equation, you have 1 plus gh of s equal to 0. Is that okay? So when you solve this, you're going to get the roots of the closed loop characteristic polynomial. So the roots of the closed loop characteristic polynomial are called the closed loop poles. Is that okay? So after solving this characteristic equation, your closed loop poles will tell you whether your system is stable or not. If your closed loop poles occurs on the right hand side of the s-plane, then your system is unstable. But if they occur on the left hand side, if all the closed loop poles occur on the left hand side, then your system is stable. Okay, so one thing about the Nyquist criteria is this particular equation over here, the 1 plus g of s gh of s equal to 0. If you solve this equation, you will have gh of s is equal to minus 1. Now this particular expression is very, very important as far as control systems is concerned, and as far as Nyquist criteria is concerned, because it helps us to understand what minus 1 means in control system. Minus 1 is very, very crucial. Okay, so the point minus 1 in control system is called a critical point, and Nyquist criteria is built around analysis of what happens in the point minus 1 comma 0, or minus 1 comma j0, or minus 1 plus j0, anyhow you want to write it. Okay, so what is this Nyquist criteria for stability of such a system whose transfer function and characteristic polynomial are defined above? So what is the Nyquist criteria? So we have 3 statements that we want to learn from to analyze Nyquist criteria for stability. Okay, so we are going to dive into the statement. Now in an exam situation, you can use any of the statement. You must not necessarily use 3 of them. Okay, if you have time, you can state 3 of them, good and fine, but I'll advise you to choose any one of the 3, and we're going to advise on the best one to choose. But it's just important to learn 3 of them. So in statement 1, a closed loop control system is stable if and only if a contour in the g h of s plane describes the number of counterclockwise encirclements of the minus 1 comma j0 points, the number of encirclements n being equal to the number of poles with positive real parts. So let me break down statement 1 so that you understand. So they're trying to tell us that a closed loop control system will be stable if the contour of this function here. So what we are going to do is, anytime we're giving a control system to analyze its stability, we are going to draw the contour or the Nyquist diagram, okay, of this function. Nyquist diagram of this function, that's what we call the contour. So if that contour encircles this point in a counterclockwise direction, okay, counterclockwise direction, what we're going to do is we are going to count the number of counterclockwise encirclements and call it n. So after counting the number of counterclockwise encirclements, we are going to count the number of poles of this function that has positive real parts. So if our control system is stable, then the number of counterclockwise encirclements has to be equal to the number of poles of this particular function with positive real parts. Is that okay? So we are going to see examples later, but for now, this is statement 1, and you should take note of it. So going down to statement 2. Statement 2 tells us that for the condition when P is equal to 0, so we still remember what N, P, and Z is. So N is the number of encirclements, P is number of open loop poles, and Z is number of closed loop poles. So closed loop poles, so these open loop poles and these encirclements. So statement 2 tells us that for the condition when P equal to 0, that's when the number of open loop poles is equal to 0. That's these open loop poles we are talking about is the poles on the right hand side. Okay, all these things, closed loop poles on the right hand side, open loop poles on the right hand side. So for the condition when P equal to 0, that means there are no open loop poles on the right hand side. The Nyquist criterion states that a closed loop control system is stable if and only if a contour in the GH of S plane does not encircle this point, okay, these critical points that we established before. When the number of poles of this function in the right hand side of the S plane is 0. So they are just trying to tell us that our control system will be stable, okay, if our contour, if our GH of S contour does not encircle this point. So if our contour does not encircle this point, then the condition for stability is that there should be no if there are no encirclement, then there should be no right hand open loop poles occurring. In other words, P has to be equal to 0. So the implication of this whole statement is that the number of encirclements will be equal to Z since P is equal to 0. And remember, the formula is N is equal to Z minus P. So if P is equal to 0, N is equal to Z. Is that okay? And when there is no encirclement of this point, then Z will now be 0 eventually. So can you see the chain relationship? So this is statement 2 of Nyquist criteria. It tells us that for our control system to be stable, right, there should be no encirclement of the -1, J0 point. Okay, so our contour should not encircle that point, and in that case, the number of open loop poles on the right hand side of the S plane has to be 0. So these are the conditions that must be satisfied for our system to be stable according to statement 2. So we are going to explore statement 3, then dive into some examples. So statement 3. Statement 3 tells us before statement 3, I just give like a little prelude. So this is the prelude. Since in practical situations only frequencies from 0 to infinity are of interest, and since in the frequency domain S is equal to J omega, now a simplified stability criterion, which is the one that we'll mostly consider henceforth, is this: that a closed loop control system is stable if and only if the locus of this function over here, G of J omega, H of J omega, or GH of J omega in a shorthand form. Okay, so the locus of this function, or the locus of G of J omega when H of J omega is equal to 1, that's unity feedback. So a closed loop control system is stable when the locus of this particular function does not encircle or enclose this point, this critical point, as omega is varied from 0 to infinity. So this is a simple statement. You can actually use this one in exam. Now I know the statement of all these things might have sounded a little strange and bizarre. That's why I created some examples so that you will be able to understand them. But before we dive into that example, let me just throw more light on what this particular stuff means. Now, when we are doing our analysis, frequency domain analysis, we know that we are supposed to check frequencies from -infinity to 0, then from 0 to infinity. We are supposed to check all these frequencies from -infinity to 0, then from 0 to plus infinity. Is that okay? So you're supposed to examine these particular frequencies so that you can know how your G of j omega and H of j omega behaves. But in practical situations, we are not interested in negative frequencies, that's from -infinity to 0. We just consider only 0 to plus infinity. And the reason we do that is because when we consider frequencies from 0 to infinity, we can assume that the behavior from -infinity to 0 will be the mirror image of whatever happens from 0 to infinity. So there is like a mirror effect, a mirror image that I'm going to show you later. Is that okay? So when we are doing our analysis, we are only focused in practical situations of frequencies from 0 to infinity. So the last statement tells us that our control system will be stable if the contour that is formed by this function does not encircle this point as we vary our omega from 0 to infinity. Is that okay? So let's look at the notice and let's look at some examples. Now, the enclosing of this point may be interpreted as the locus passing the left hand side of this point. Is that okay? So this is the G of j omega and H of j omega locus that we are talking about, and this particular locus is called the Nyquist diagram or the Nyquist plot or the frequency response plot. Okay, let's dive into our examples. So we now want to illustrate Nyquist criteria proper. So let's start with this diagram. So starting with this diagram now, if you want to understand Nyquist criteria, assuming this is your GH of S, okay, so this is your open loop transfer function. So this is the representation of G of S. Now, I'll show you how to draw these diagrams later, but for now, this is the contour that is described. This whole stuff is the contour that is described by this particular function when we vary our omega from -infinity to 0 to infinity. So when we vary omega from -infinity to 0 to infinity, then the graph will be like this. So the main one we are interested in is when W is 0 to when W is infinity. I'm calling W, but it's omega, but pardon me for now. Now, when you draw the plot of this function, the Nyquist plot, the graph from omega equal to 0 to omega equal to infinity will turn out like this. So you can see this curve. It's an asymptotic curve. It doesn't necessarily touches the y-axis, so it goes like this. So what happens to the contour from -infinity to 0 is just a mirror image. So the one in dotted line is just like a mirror image of what we are seeing. Okay, this one in bold line. So the one in bold line is when W is 0 to when W is infinity. Then the one in dotted line is when W is 0 to when W is -infinity. Is that okay? So this is it. So what we normally do is we just focus on W equal to 0 to W equal to infinity. After drawing the graph of W equal to 0 to W equal to infinity, we'll now use the mirror image of W equal to 0 to W equal to infinity to replicate W equal to -infinity to W equal to 0. So someone can say W equal to -infinity and omega equal to 0 is this one with dotted lines. So this that you're seeing here is just like a mirror image of what's happening on the right hand side. On the left hand side, you see the left hand side has this contour like this, and the right hand side just has like a mirror image of it. So overall, whenever you draw the contour of a particular open loop transfer function, you're going to have something like this. You're going to have some encirclements like this. Now, assuming this point is -1, 0, okay, this is the critical point that we are interested in. So we now want to study the stability of this system using Nyquist criteria. So what is the value of n Remember, n is the number of encirclements of this point. I'll now ask myself, how many times does this locus encircle this point? There is no encirclement, so n is equal to 0 in this case. So what is the value of p? P is telling us the number of poles, okay, of this particular equation that are on the right hand side, or the number of positive poles. Now if you solve this characteristic equation, you're going to get, by equating this denominator to 0, yeah, you're solving for the poles. The poles of any transfer function is by equating the denominator to 0. So equating the denominator to 0, s will be equal to 0. You now have s will be equal to, when you solve this one, you get minus 1 over t1, then s will be equal to minus 1 all over what? T2. So there are 3 poles, and as you can see, none of these poles occur on the right hand side because all of them are either 0 or they are negative. Is that okay? So the value of p, which is supposed to be the number of poles on the right hand side, had it been we had a positive value for s, it would have been the value of p. I would have counted it, but this time around there is no positive value of s, so that means all poles are negative or 0, or all of them are situated somewhere in the left hand side of this plane. Therefore, number for p will be 0. There is no right hand poles, or there is no unsteady poles here. Then the number of z, according to the Nyquist formula, z is equal to n plus p. So z gives us the value that will eventually use to determine whether the system is stable or not. So in this case, we have 0 plus 0. So z is equal to 0 eventually. So since z is equal to 0, remember z is considered as the number of number of closed loop poles. Is that okay? Number of closed loop poles. So the number of closed loop poles is 0. So it means that the stability of the closed loop system is guaranteed, since the number of closed loop poles to the right hand side of this plane has been determined as 0. Now the beauty about the Nyquist criteria is that it helps us to evaluate the stability of the closed loop system without having to use 1 plus gh of s to form our characteristic equation. Or remember, the closed loop transfer function is this, so we don't have to do this stuff when we are using Nyquist criteria. In some other systems, you will have to replicate this equation, like your g of s divided by 1 plus g of s h of s. You will have to do this and do some simplifications. But with Nyquist criteria, okay, you don't need to do this. Now let me tell you something about this particular equation over here. This equation over here, the denominator of this equation, if you equate the denominator equal to 0, the roots that you will get by solving this equation is actually z. Is that okay? The roots will give you what we call z, or the number of poles. Is that okay? Closed loop poles. But because we are not using 1 plus g of s, which can be very difficult, we are just using the formula. So all we just need to do is that in order to determine z, we just need to know the Nyquist plot. We need to draw the Nyquist plot, and we need to know the number of this, like an open loop equation characteristic, open loop transfer function. We need to know the number of positive open loop poles. So in this case, there are no positive open loop poles. All of them are negative or 0. So if we know the number of encirclements and the number of open loop poles, we can easily find z, which is the number of closed loop poles that will probably occur on the right hand side of the equation by adding n and p. Is that okay? And it will give you what? 0. So since z is 0, the comment is that this system is stable. Okay, so someone can say the system is open loop marginally stable because one root occur on the origin, s equal to 0. So any roots that occurs on the origin will render the system marginally stable, irrespective of the fact that some roots occur towards the left hand side of the plane. Now the open loop transfer function is marginally stable. Then the closed loop transfer function, okay, has now been determined to have 0 poles occurring on the right hand side. So we are not really interested in the open loop behavior. The closed loop behavior is what we are interested in, the closed loop stability, and eventually this system is going to be stable since there are no what poles occurring on the right hand side for the closed loop characteristic equation. So I know it's sounding strange, but let's go to the second example and we'll try to solve it together. So this is another system now. So where you have your open loop transfer function to be KB all over this. As you can see, what the examiners do is they either express the transfer function in the standard form, standard time constant form, or they will express it in a form and expect you to convert it to time constant form, but make sure you try to convert it to time constant form. Now, if you draw the Nyquist diagram for this particular system by varying your omegas from 0 to infinity and 0 to minus infinity, this is what you get. This is the entire plot. Now take note, this one is the same with this one. The only difference is that the coefficient multiplying k is a in the first case, while the coefficient multiplying k is b in the second case. Now the multiplication of this coefficient k by b has now make our plot to encircle this point. So we are now going to determine the number of encirclements. So determining the number of encirclements n, you can see that the number of encirclements of this point minus 1 comma 0 is, there is a cycle. The first cycle is this one. So we are, remember, always take clockwise encirclements. There is a convention. Clockwise encirclements should be positive, while anti-clockwise should be negative. So if you're studying Nyquist diagram and you discover that your clockwise encirclement is positive, right? You give it a positive sign. Your clockwise encirclement is actually in a clockwise direction. That's what I meant to say. You give n positive, but if your encirclement is in an anti-clockwise direction, and n will be negative. So since the encirclement of this point by this first one over here is clockwise, so this is one encirclement, so that's one. Now there's another encirclement by this diagram here, this one, okay, that you're seeing. So the first encirclement is this one over here, then the second encirclement is by this other bigger one over here, these other bigger contours. So there are two encirclements. So we're now going to ask ourselves, how many poles are on the right hand side? How many open loop poles are on the right hand side of the S-plane? If you solve for the open loop poles by equating the denominator to 0, S1 plus T1S and 1 plus T2 S equal to 0, you get S is equal to 0, S is equal to minus 1 over T1, and S is equal to minus 1 all over what? T2. So there is no open loop poles that is positive, or in other words, occurring on the right hand side. So the value of P is equal to 0. So at the end of the day, Z is equal to N plus P. So that's 2 plus 0, and that's 2. So with Nyquist criterion, we have been able to determine that the number of closed loop poles that will probably be on the right hand side of the S-plane is 2. So the conclusion is that this system, or this arrangement of system, since Z is equal to 2, is unstable. Okay, so the condition for our system to be stable is that Z has to be 0. Okay, Z has to be 0 and only 0. If at all, the system will be 0. Z, remember, is the number of open loop, closed loop poles. I keep mixing them up. Z is the number of closed loop poles that are positive to the right hand side of the S-plane. So we use the value of N and the value of P to predict the value of Z. So that's all about the Nyquist theory. Z is equal to N plus P. We can determine the number of encirclements and the number of open loop poles from what is given to us. So with the number of encirclements and number of open loop poles, we'll be able to determine the number of Z, okay, by using this formula over here. And for stability, Z must be 0, but if Z is anything other than 0, then your system is unstable. So this arrangement of system is unstable. So let's look at the third one. So you can pause the video and try to solve this third one by yourself. Okay, so when you're done with solving it, you could actually unpause the video and let's see if we'll get the same thing. Okay, let's go. All right, I assume you must have paused the video and I'm going to solve it. Now, looking at this system, this g of s equal to kc all over this stuff has a contour that is represented like this. So this is the contour, or this is the Nyquist plot for this system. So you don't have to be scared. I'll show you how to do Nyquist plot in another video. It's quite easy and straightforward, but it will also help if you can memorize some of these forms, how their Nyquist plot is going to be, just in case in an exam scenario you're kind of like rushing or dealing with time. If you memorize some of these standard forms and their Nyquist plots, you'll be in a very, very, very safe place. Okay, so the Nyquist plot for this system is what we have here, and you can see that the Nyquist contour has encircled that critical point -1, 0. So what we asked ourselves is, how many times was it encircled? So the first clockwise encirclement, clockwise, is going in this direction. So this is 1. Then the second one is by this other bigger one, okay, going in this direction. So it goes like this, it continues like this. So there are 2 encirclements of the point -1, 0. So n is 2. So what is the value of p? As usual, if you solve for the poles, remember p is open loop poles. By equating this denominator to get to 0, you get the open loop poles. You get s is equal to -1 over t1, -1 over t2, and -1 over t3. So all the open loop poles are negative. That means they are on the left hand side of the plane. So if they are on the left hand side of the plane, what does it mean? It means that there is no right hand poles, because what you're using as p is not, some people will say number of poles is 3. No, that's not true. P means number of positive poles, or number of poles that occur on the right hand side. Do you get that? So when you solve your characteristic equation and you find out that there is a value that is positive, so you will count the number of positive values of s, and that will now be the value of p. Since all these ones are negative and there is no pole occurring on the right hand side, now that we know the value of n and the value of p, we now want to find z, which is going to be the closed loop poles. And if you remember the formula, z is equal to n plus p, that's 0 plus 2, which is going to be 2. So the conclusion is that this is unstable. Okay, since z is 2, it means that the number of closed loop poles on the right hand side of our S-plane is going to be 2. So we don't want any closed loop poles to be on the right hand side. We want everything to be on the left hand side. In other words, we want Z to be 0 for stability. So that's Nyquist criterion. If Z is not 0, then your system is not stable. Okay, so let's look at another one. Yeah, so one thing that you say, you can also make some comments about the open loop transfer function. The open loop transfer function has all the roots on the left hand side because they are all negative. So you can say the open loop transfer function is open loop stable, but the overall system is closed loop unstable. So how you're going to use to judge whether something is open loop stable is, if it's open loop stable, then p will always be 0, okay, because there is no poles on the right hand side. Then if it's closed loop stable, z should be 0 too. But if the reverse is the case, where z is not 0, then we'll have closed loop unstable. And when p is not 0, we'll have open loop unstable. Is that okay? So we're going to move on to another one by rounding up. I just want to do as many as possible. So look at this one. So when you draw the contour of this beautiful transfer function, open loop transfer function over here, if you draw the contour, you're going to get it like this. So this is the contour okay, for w equal to 0 to w equal to infinity. Now, to get this other dotted line contour, which is w equal to minus infinity to w equal to 0, all we just need to do was to replicate the mirror image of this first one. So this is the first one from 0 to infinity. So to get from minus infinity to 0, you just do the mirror image, okay, and you get it. So this becomes your contour. Now this is the point minus 1 comma 0. We will now ask ourselves, how many times does this entire contour, or the contours described above, how many times does it encircle this point? You see that there are no encirclements because the contours are to the right of this point. So we'll ask ourselves, how many open loop poles do we have that are positive, or open loop poles to the right hand side? We can find out by setting this denominator to 0. That will give me s is equal to minus 1 over t1, minus 1 over t2, and minus 1 over t3. Okay, so we can see that all these open loop poles are actually negative, so none of them are positive or none of them are occurring on the right hand side. So the open loop poles is 0. So in this case, our z is going to be n plus p, which is going to be 0 plus 0, which is 0. So the system is open loop stable in the sense that all the poles are negative. Then it's also closed loop stable. Okay, it's closed loop stable, and eventually it's stable. The stability of our system depends on the stability of the closed loop system. Every system has like an open loop version and a closed loop version. So the final stability of the system is not necessarily determined by the stability of the open loop system. It's actually dependent on the stability of the closed loop system. So that's what you use to judge the final stability. So since z is equal to 0, the system is closed loop stable, and overall it is stable. Is that okay? So let's look at another one. So looking at another one, if you draw the contour for this function over here, you're going to get it like this. Okay, so when you draw the contour of this function, you get it like this. So for values from 0 to infinity, we will have the contour moving like this. Then for values from minus infinity, omega equal to minus infinity to 0, we're going to have the mirror image. So it's actually now something different, because this time around the contour is in an the direction of the contour is counterclockwise. Okay, all the ones we've been seeing has been clockwise, as you can see, clockwise. So you have the first encirclement in the clockwise direction, then second encirclement follows this part in the clockwise direction. But this time around, because of this system like this, the minus 1 comma 0 point is encircled in a counterclockwise direction. So we can now see that the number of encirclements, there's actually one encirclement of this point, but since the encirclement is counterclockwise, I'll call it minus 1. Is that okay? So another thing I need to take note of is that I need to ask myself, what is the value of p? That's the number of open loop poles on the right hand side, on number of open loop poles that are positive. If you solve this equation by equating the denominator to 0, 1 minus 1 plus ts equal to 0 imply that s is going to be plus 1 over t. So that means s is positive. So the only pole of this system is positive. Okay, that means there is one positive pole from the open loop transfer function, okay, that will occur on the right hand side. So what is the value of z? The value of z is actually what? N plus p. So you can see that n plus p is minus 1 plus 1, and which is 0. So since the number of counterclockwise encirclements is equal to the number of poles, according to the first statement, number of counterclockwise encirclements is equal to the number of poles. So the counterclockwise makes us use minus 1 here. So when we added it according to Nyquist theorem, we see that z is equal to 0. So z is equal to 0 means that our system is stable. Okay, our system is stable. So although it is closed, it is open loop, unstable. Open loop unstable. Why? Because P is equal to 1 instead of 0. That means there's one pole on the right hand side. But since the overall system has Z equal to 0, which is the closed loop poles, that's the closed loop poles occurring at the right hand side being 0, means that there are no poles of the closed loop system occurring on the right hand side, making the system eventually stable. Is that okay? So this is statement number 1, where we said that whenever we have any control system, the number of counterclockwise encirclements should be equal to the number of what? Open loop poles. So let's just flash to that statement 1 again, where a closed loop control system is stable if and only if the contour in the G of S plane describes a number of counterclockwise encirclements of this particular point such that the number of encirclements n is equal to the number of poles, okay, with positive real parts. Number of poles of this equation with positive real part. So we've just seen that the number of encirclements, counterclockwise encirclements, is actually equal to the number of what? Poles. So in terms of magnitude, it's 1 1, but we have to put this minus sign to show that it's a counterclockwise encirclement. So we're going to look at the last system and judge its stability. So look at this last system and tell me what you think about the stability of this system. Is it going to be stable or unstable? All right, so thank you. Let's do that together. So you can see that the contour, okay, described by this function, the contour of this function is what you're seeing here. So the contour from 0 to infinity is this one that you're seeing. If you vary your, after you put s equal to j omega, g h of j omega will be kf divided by minus 1 plus j t omega. So when you start varying omega from 0 to infinity, you find the locus of the path traced like this. So that is what it means. So you don't need to vary omega from minus infinity to 0 when you could just use the mirror image. So this is omega equal to minus infinity to omega equal to 0, which is the mirror image of what we have down here. Is that okay? So since we have it like this, we now see that this contour does not encircle this point. So the number of anti-clockwise, remember the contour is also moving in an anti-clockwise direction, mostly because of this minus 1 over here. So the number of anti-clockwise encirclements is 0. Is that okay? But let's solve for the number of poles with positive real parts. So the number of open loop poles with positive real parts, equating this guy to 0, you will get minus 1 plus ts is equal to 0. It implies s is equal to plus 1 all over t. So this means that there is one pole with a positive real part. Okay? One pole with a positive real part. Then my z is equal to n plus p, which is 0 plus 1, which is 1. So it means that the system is unstable. So the system is unstable because irrespective of the fact that the contour does not encircle that point, we still have what? One open loop pole that influences our final decision. So making the total number of closed loop poles 1. Okay, so the total number of closed loop poles 1. So the system is unstable. So another way, like I was trying to say, there is another way to get the total number of closed loop poles without using this formula, and that other way is you have to express the system as g all over 1 plus g h. So when you express the system in this form, you're now going to solve this characteristic equation d of s 1 plus gh, and you equate it to 0. So when you solve this characteristic equation, this is the closed loop characteristic equation, okay, while the open loop characteristic equation is just the denominator of g of s. So there's a difference between the open loop characteristic equation and the closed loop characteristic equation. The open loop characteristic equation, okay, the open loop characteristic equation is just simply equating the denominator of g of s to 0, and the open loop characteristic equation yields the open loop poles. But the closed loop characteristic equation is when you express the system in this form, G all over 1 plus GH. Okay, 1 plus GH. Then you will now solve the denominator. You solve for this one. Okay, and you solve for this one and you equate it to 0. Whatever you get, that's your characteristic equation, and we call it the closed loop characteristic equation. And the roots of that characteristic equation will give me the number of poles that are either positive or negative. So assuming we were to solve this question using this same format I just described over here, if we express it as G over GH of S, we'll be having something like G, we'll be having something like K F all over minus 1 plus TS into 1 plus, you now have KF all over minus 1 plus TS. You will have it like this. So if you do the math, you will have KF all over minus 1 plus TS divided by, if you do this, you get minus 1 plus TS plus KF all over minus 1 plus TS. So these two will cancel out, leaving you with KF all over minus 1 plus TS plus KF. Okay, so this is going to be my G all over 1 plus GH. Okay, so this will be the new transfer function. So if you equate the denominator of this new transfer function to 0, we call it closed loop poles, solving for the closed loop poles. So this is the closed loop transfer function, while this is the open loop transfer function. You can see the open loop poles is equating this one to 0 and solving, and the closed loop poles is also what equating this one to 0 and solving. So let's see if we can do it. If we equate minus 1 plus TS plus KF to 0 and solve for S, since KF is a constant, we'll have S is equal to 1 minus KF all over what? T, something like that. So you can see now that S will have one particular pole. Is that okay? So the problem is that we don't really know whether this pole will be positive or negative, but this pole will be negative if the multiple of K and F is less than 1. But if the multiple of K and F is less than 1, the pole will be positive, sorry. But if the multiple of K and F is bigger than 1, the pole will be negative. So you can see that this method of expressing it into closed loop transfer function format will not really elucidate on the final sign of the pole, of positive pole, because we'll be left with a lot of unknowns. That's why the that's the Nyquist and Cauchy's principle is more reliable in helping us to analyze the stability. So we just need to draw the Nyquist plots, then find the number of open loop poles that are positive, and after that we can now interpolate for Z by using the formula n plus p. So if Z is 0, the system is stable, but if Z is not 0, then the system can be regarded as unstable. Is that okay? So this brings us to the end of Nyquist criterion. I know it was a long video, but I hope you grab the gist now. I hope you understand it. I hope you can really apply it to solving problems that may occur in the future and to testing the stability of systems. So in the next video, we'll learn how to draw the Nyquist plots, and we'll learn how to note some important things about the Nyquist plot, such as phase margin, gain margin, and phase crossover frequency and gain crossover frequencies. So like this video and check out the next video in the playlist to understand how to do those ones. Thank you and stay blessed.